Okay, so just to finish off our discussion of the index theory, uh, we invoke the following theorem. It was continuation only. Any closed curve, I should say any closed trajectory, on R square must enclose fixed points. Whose indices add up to +1. So the trajectory enclosed, the indices of the fixed points, this is a closed trajectory, and the indices should add up to +1. So this is kind of interesting because using this one can rule out potential closed trajectories based on this theorem. So as an example, we consider a phase portrait of a double well which had 3 fixed points. One of them is a saddle, so this is one of the wells, and so this is like a double well, not drawing it very well. So, and then of course there are some trajectories like that. So these are the closed trajectories, and then there's a trajectory that goes like this, this. So this would be, sorry, I got the arrows wrong. I'll have a trajectory this way. So starting from this particular point, I'll have going this way. This is an unstable fixed point. So over here I have -1, over here I have +1, over here I have +1. So this is the trajectory, and if you can look, the kind of fixed point, so for example this trajectory is allowed because it was +1, -1, +1, so the net index is +1. So this is allowed. This can occur potentially, it's certainly not ruled out, and one can see why. You can divide this into 3 parts. So you have IC as IC1, C1, C2, C3 plus IC2 plus IC3 and that comes out to be plus 1. Similarly, a trajectory enclosing just two fixed points, this is ruled out. As the theorem says that the index has to be the sum of indices of all the fixed points has to add up to plus 1. So think about why should this theorem actually be true. Why do you expect such a theorem to hold? But as an application again, so we had this phase portrait of the rabbits versus sheep problem, which was the population of rabbits and out here I had a saddle point, remember, in this phase portrait. Here was a fixed point. These were the rabbit. These were the sheep. Here was another fixed point, these lines, and this was an unstable point. So immediately one can rule out there is no closed orbit. What about here? Well, technically there can be a closed orbit because this was a stable node, this is plus 1, but the closed orbit would pass through this invariant line, which is actually pointing over here. So this is also ruled out. I can't have a closed trajectory pointing this way. That would violate non-uniqueness because this point is invariant. This points towards this. Similarly, this is ruled out, even though my theorem says that this is plus 1. And similarly, this is ruled out because the closed trajectory here, if it points over here, this invariant line points here. So this is also ruled out. So a combination of the theorem that the closed trajectory has to have the fixed points whose indices should sum to plus 1, using invariant manifolds, and the theorem, one can rule out fixed orbits or closed orbits, so to speak. So this is actually a generalization of this theorem can be generalized, and this is a topology plus vector fields. We just had a glimpse of it in the plane, but there exists a very interesting field in higher dimensions about such things. So for example, there is this theorem called as the hairy ball theorem, which is to say, imagine my phase space is the sphere and I have a vector field. It's like chocolate dripping over it, like this, over a sphere. So essentially what it says is that if I make a loop around it, that would be plus 1, and here is a sink, that's also going to be plus 1. So if I am following the vector field, any vector field, if I follow it like a trajectory on the sphere, vector field, it has to have closed trajectories that plus 2 for the sphere. So if there is a source there, so this is also called as the hairy ball theorem, or in some sense it's also called why is it called that? cannot comb. Imagine this was a ball with hair, the direction of hair representing the vector field. So the idea is that you can't comb a sphere with hair without avoiding fixed points. But indeed, you can comb a torus. On the torus, you can comb a torus. So this might be one of the reasons the tokamaks or the particle accelerators are designed in the shape of a torus, because indeed you can follow, the particles can follow a trajectory without a source anything, and they can just rapidly accelerate. And I'll just briefly mention, this is all a part of generalizing this to higher dimension. The general theorem is that the sum of indices should be 2 minus 2g, where g is the genus of the surface, or in other words, the number of holes on a surface. So the genus of a torus is certainly 1. There's one hole. G equals to 1. So indeed 2 minus 2 is equals to 0. So you can have a vector field which closes in on itself without having the requirement of the index to be plus 2 like a sphere. Certainly there can be surfaces like melting two toruses. Over here the genus is 2. And this theorem is called as the Poincare-Hopf index theorem. There's a generalization what we already know in one of the dimensions, in the 2D dimension, R2 dimension. So Poincare-Hopf theorem is a generalization of this guy. Okay.